Hello, welcome to our 21st lecture. We're talking about relative extrema today. Last time we talked about increasing and decreasing functions, and we'll see now why do we care about such things. Well, extrema is referring to extreme values. Extrema is plural for extreme. So think maximums and minimums, these extreme values on your function. Okay. So it is often useful to find maximum or minimum values of functions. So that's where this word extreme comes from. So think, for example, about profit. Say we have a problem where we have a profit function. Well, we would like to maximize that profit, right? Makes sense. You want to make the most money. And think about cost as well. If we have a problem with the cost function, we would like to minimize that cost. So this is not some useless mathematical exercise. It's very important to be able to find maximums and minimums. So let's define these things. Let C be a number in the domain of a function f. So it's a valid x value that can be plugged in to this function. Then f of c, the y value, so I'm going to use the word relative. That's what the textbook prefers. So that's what I'm sticking with a lot of the time. But there's also a word local, which personally I prefer. I think I'm going to use both. Pretty even mix. So relative or local maximum, let's just focus on that first. So this y value, f of c, is a relative or local maximum for the function f. If there exists an open interval so we have an open interval that exists a, b, which contains that x value c. And so these are x values, and our special x value c is in there. So we can find some open interval like this. Such that f of x is less than or equal to f of c. And what is x? Well, this is for all x values in that interval. So c is a certain x value. It's in the domain of your function f. And then f of c, a y value, is a local or relative maximum if you can find an interval which contains c where all other y values in the interval are less than f of c or below it. So just a little picture. Let's draw a curve like this, represent my function f, and let's focus on this point right here. So it's at the x value c. Now this y value here that we're at, f of c, of course here I'm graphing y equals f of x. So that y value is a local maximum or a relative maximum because I can take an interval which contains c in it, from a to b, and we'll look at that. This is the highest y value inside that interval. And that's why I like the word local, because it gives you a picture of this nearby neighborhood. This is the biggest thing in that neighborhood. That's the idea. So it's a local maximum. Notice we have stuff way over here, which goes up higher. That curve goes up forever. But that's not really what we're concerned about. We're just concerned about what's happening locally in that nearby neighborhood. This is the tallest point. Now, similarly for local minimum or relative minimum, I won't write as many words this time, but it's very close idea. If you have all the same stuff, but now all other y values are greater than or equal to f of c, that's when you have a minimum. Okay, so maybe I'll make a smaller picture here. So right here is C. It's this low point. And I can find a neighborhood, some interval from A to B, which contains C, and this f of C, this y value here, is the low point within that little neighborhood. So that's a local minimum. Okay, now things get a little complicated if your domain gets suddenly cut off for your function. So if C is an endpoint, in the domain of f, so think like a closed interval, and right at the end, your domain suddenly cuts off and you have this endpoint. So in that case, we only consider one of the sides. So I'll say we only consider the half open interval, the part that is in the domain. So if I may provide a quick example of this. Let's look at the square root function. Now, I'm not really adding anything special here. This is just always true with the square root function. You cannot plug in negative numbers. So the domain is just positive numbers and 0. And this is a closed interval, by the way, or well, at least one of the sides, but that's what counts. Right, that means the same thing. So just a rough sketch of the graph of the square root function. It stops very suddenly at the origin. Square root of 0 is 0, but then you're not allowed to plug in any negative numbers. So you just stop there. That's an end point. So we still consider this to be a local minimum. It's still the smallest guy in its neighborhood. It's just that we're only open on one end because you can't really go open over here. There's nothing over here. So that's what we mean when we have an endpoint. We're only worried about open intervals from the other side, the part that's in the domain. Or I guess I'm doing a, whoops, tick marks here, and showing my interval up there. But this is the lowest one in its neighborhood. Okay, well let's graph a more complicated looking function, and we're going to determine just by looking at it what are the relative maximums and minimums. So you might see wording like this: identify all relative extrema, meaning maximums or minimums, identify all relative extrema on the graph. And I'll need to be a little precise with my picture. So I'm going to say this is height 3 right here. 2, 1, 0. That's not very evenly spaced, is it? That's a little better. Okay, I don't want to be spending all day doing that. Okay, so 3 to the left, let's do. And let's go 3 to the right as well. And we're going to go 1 down. Okay. So let's draw a point here at -3, 3. And we'll drop down to -2, 1, the straight line. And let's have a curve that just touches up here on the y-axis, then goes back down. We cross right here when x is 2. And all right, let's say when we hit 3 as my x value, we reach this height of -1. And then we go back up. All right, so there's a somewhat accurate picture. And we want to find all relative extrema, or local maximums, local minimums. Okay. Well, I'd say this one stands out to me. You can make a little neighborhood here, open interval. And within that open interval, this is the low point right here. So that's a local minimum. Okay. So let's say, maybe I'll write it over here. We have a relative minimum I'm abbreviating. Now here's the way that you say it. You say that the minimum itself is the y value. So the minimum value is 1, because that's this height right here. But then you say at x equals -2. So again, the minimum value itself is the y value, but then you say it's at a certain x value. Okay, that's one of them. And well, if we look over here, notice I can make a little neighborhood, an open interval, and I have a high point. At least it's supposed to be right there. So that is a relative maximum. So the maximum value itself is the y value, 3, but at x equals 0. Now, before I move on further to the right, I might notice this right here. Notice that I did not draw an arrow there. So I'm saying that this is a proper endpoint. We're not just going on forever upward like we have over here on the right. So this is an endpoint. And that means that when I'm looking at these neighborhoods, these open intervals, well, we really just need to look from one side. And this is clearly the high point in that little area. But hey, notice it's also the same. That same maximum value of 3. So we can just throw that in there, that other x value. Okay, further to the right. So we still haven't taken this one yet. I have a relative min of height -1 at x equals 3. And that's it. That's all the relative extrema. So I want us to notice something about all of these points where we have an extreme value. So we'll notice in the above example that all, and now I'm switching to that language of local. Local and relative, they mean the same thing. So all of our local maximums and minimums, they occurred at some very special places. So at certain x values, we'll call them C. And now I'm going to list some things, but this list may look familiar from the previous video. So for one thing, in some of these places, the derivative was 0. And you can tell by looking at tangent lines if you draw them. Right there, that's a horizontal tangent line that just glances the curve. So that has slope 0. The derivative is 0 at that point. And likewise with this one down here. So the way that you can tell the derivative is 0 just by looking at it, it's where you have this smooth hilltop or the smooth valley shape. So at all of these relative extrema, for one thing, you could have the derivative be 0, but there's more that can occur. Could be that the derivative does not exist or is undefined. That's a D. And that is occurring at this one right here. Remember, that's always what is happening when you have like a corner or cusp like this, a very sudden, sharp turn. It's because the derivative is a limit, and limits must agree from both directions. So coming in from the left, the derivative is this negative slope of a line. But on the right side, it's a positive slope. So there's disagreement on the derivatives from each side, so there is no true derivative at that point. So notice here that f prime of -2 does not exist. So at every extreme value that we had, either the derivative was 0, or the derivative didn't exist, or we had an endpoint. And that list should sound familiar from last time. Let's say, or C is an endpoint. In the domain. That sounds a lot like critical numbers to me. That's exactly what these are. So this leads to a nice little fact. That whenever we have a local or relative max or min, it must always occur at a critical point. Remember from last time, critical points are places where the derivative is 0 or undefined or an endpoint. And that's exactly what I've listed out right here. So, relative extrema always occur at critical points, but I'm going to offer a word of warning that you can be tempted to think that this goes both ways, and it does not. So, a word of caution, this does not hold the other way. So, what I'm saying is that just because you have a critical point, that does not necessarily mean that you have a local maximum or a local minimum. But the reverse is true, that if you have a local maximum or minimum, it's at a critical point. So let me say just because you have a critical point, that doesn't mean you have a local max or min. And I'll show you an example in a little bit. But what you can do, what can be useful, is to think of these critical points as candidates. So they're potential relative extrema, but they might not be actually those things. But they're your candidates. So we think of it as a candidate for a local maximum or local minimum whenever you have a critical point. But it's not a guarantee. So in order to figure this out, we have to do a test. And we call this the first derivative test. Why am I using that word first derivative? It's actually not because, well, not just because this is the first test we're talking about. This word first has a special meaning for derivatives, and that's for a future video. So that's a little teaser there. So this test will allow us to classify critical points. And this is based on where the function is increasing or decreasing. So there's a reason we talked about it. When I say classify them, I'm talking about, this is a relative maximum or this is a relative minimum, or possibly neither. So here's how you tell. Last time we were drawing our little number lines, and I'm going to do that again. So suppose we have a critical point C, so I use that to divide up my number line in x-axis. And suppose that the derivative is positive on this side of C, negative on the other. Well, that means that my main function f is increasing, and then you hit C, and then you're decreasing. So this is when x is C. So we're increasing, then decreasing. Well, when you draw it out like this, you can tell that this is a local maximum, just by looking at it. So local maximums occur when you have a critical point and you're increasing on the left side, decreasing on the right side, as we see in the picture here. Well, if you have the opposite occurring, then that means I'm decreasing, f is decreasing until I hit C, and then increasing, so we're going down, then up. And you can see here, this is a local minimum, it's a low point. But you actually can have things occur where, say, you're increasing on both sides, so the derivative is positive on both sides of C. And that's going to look something like this. You're increasing until you hit C, and then the derivative is 0, perhaps. So we flatten out, but then you just start increasing again from there. So this can happen. A good example would be like x cubed, that function. So this is neither a maximum nor a minimum, because if you look on the left side, this is above all that. But whenever you try to take a full open interval, including this, you're going to have a mix. It's in the middle. Right, so it's neither a high point nor a low point. So that's why I say that not all critical points are maximums or minimums, but they are your candidates for them. You just have to do the first derivative test to check. Okay, then the other thing that can happen is we're decreasing on both sides, hit a critical point, but then still decreasing. Oh, this is at C, by the way, just to be clear. A good example of this one would be like the graph of negative x cubed. Well, it's supposed to be flat here. That doesn't look perfect now, does it? There, that's a little better. Okay, so my recommendation when we hit exam time is don't just memorize these. You will need to know them, but when you study, I would say don't just memorize that, oh, if it's plus then minus, that means maximum. I encourage you instead to think about the picture here. Your function is increasing and then decreasing. That tells you that your critical point is like a hilltop and it's a maximum. So when you're studying, think in terms of these pictures, be able to do that thought process in your head instead of blindly memorizing these. Just my word of advice. Not that I'm totally against memorization, but yeah, it's good to understand the why behind these things. All right, finally, let's do some real functions with these expressions. Now that we have first derivative tests, we don't even need graphs to find these maximums and minimums. So we use the first derivative test. Use the first derivative test to find all relative extrema. And let's start with the polynomial. X cubed minus 3x squared minus 9x plus 17. So we're not going to graph it, but we will use the first derivative test, and that will be by finding the critical points first. And then those are the candidates for finding these relative extrema. So finding critical points greatly narrows down our list from infinitely many real numbers to choose from, to just a few. So there's the derivative. And if we're looking for critical points, we want to set this equal to 0 to see where this is 0. This will always be defined. It's a polynomial, and there are no endpoints. So this is the only thing to look for. When is this 0? Well, it helps to factor first. And this part can yet be factored. That would be a minus 3 and a plus 1. Okay, now I say that this is set equal to 0. And we see that the critical numbers, that's just the x values, are when x is 3 and negative 1. So these are the critical numbers which have the potential to be relative maximums or minimums. So let's divide up the number line to do the first derivative test. So these are x values, and I'm seeing how the derivative behaves. 1, 2, 3. There's a critical number, and a -1. So I want to see, is the derivative positive or negative in these sections? So we pick test points. Just plug in some point, and that whole block is going to behave in the same way. So f prime of -2. Well, here's my factored version of f prime up here. So -2 minus 3 is -5, and -2 plus 1. Well, the most important thing is that this is a double negative, so we're positive. The derivative is positive in this entire section. Okay, let's use 0 as a test point. So let's zoom out a bit. Plugging in 0 into the derivative, get -3 and 1. So this will be negative. Now we might have an alternating pattern, that's most likely, but you do have to check. Plug in 4. And that is indeed positive. So let's just look at this critical number of -1. The derivative is positive on the left side, but negative on the right side of it. So that means my function is increasing and then decreasing afterwards. So that represents a maximum. So we have a relative maximum. I'm going to say of 22. I'll talk about where I got that. But it's at the x value -1. 22 is just the y value when you plug -1 into the original function, into f. Remember, the maximum value itself is the y value, but it's at this x value. We look at this other critical number of 3. Well, my function is going down until it hits 3, and then starts going up again. So that's a low point. It's a dip. We have a local minimum at 3. So we have a relative min of -10 is what I got. That's just plugging 3 into the original function. And we know that this is it without even graphing. This is because if you're going to have a relative max or a min, it must be at critical points. And we just classified them all. So this is it. We have time for one more example. Make it perhaps a little bit more difficult. just going to say this in a different way. Find the local maximums and minimums, all of them, of the function f of x equals x minus 1 to the 2/7 power. Okay. So first order of business is to find critical points or critical numbers. They're almost the same thing. And we want to start by taking the derivative. Notice that there are no endpoints with this, by the way. This is completely defined, as I'll show in a little more detail in a bit. But when you have this rational exponent over 7, that means I'm taking a 7th root. And whenever you have your index being an odd number, like a cube root or 7th root, then in that case, anything can be plugged in. It's when the index is even, like a square root or a 4th root, that's when you run into problems with your domain, and you're not allowed to plug in negative numbers. So I'm saying here that's not an issue. So the domain is never cut off. I can plug in any x that I want to. That means my critical numbers will come from where is the derivative 0 or where is it undefined. Okay, notice that this is chain rule. I have the x minus 1 expression inside the 2/7 power. So I take the derivative of the outside part first. Doing power rule, I bring the 2/7 down, and I subtract 1 from this old power, which will get you negative 5/7. But then by chain rule, you have to multiply by the derivative of the inside. Well, that's just 1 in this case. All right, let's simplify this a little bit. This is 2 over 7. Notice I've got a negative exponent, so I'm bringing that down. So an x minus 1 to the 5/7. Or it might be even more convenient to write it as a root. This is the 7th root of x minus 1 to the 5th. So there's the derivative. And remember, I'm trying to find critical numbers. So will this thing ever be 0? And the answer is no, because the numerator will never be 0. And whenever you have a fraction like this, that's all that matters, is the numerator 0. That's what makes the whole thing 0. So f prime of x is never 0 because of the numerator. Let's say because the numerator is never 0. It's just 2 all the time. But can this thing be undefined? And the answer is yes, because while the 7th root itself is okay, this thing can still be 0, and then we're dividing by 0. So that's the thing that can happen. This derivative is undefined when the denominator is 0. And so because the seventh root itself is pretty well behaved in this regard, this is the only issue we can look for. So this is the only place that we're going to get a critical number. So I'm going to take that denominator and set it equal to 0. And try to solve for x. That will make the derivative undefined. So first off, I can divide both sides by 7, which doesn't affect the 0. So then we get the seventh root of x minus 1 to the fifth is still 0. But then I can take both sides to the 7th power. Notice that also doesn't affect 0. So the derivative is undefined when x minus 1 to the fifth is 0. And notice that we're pretty much done here because this is already factored. The only critical point, or the only critical number, is 1. So this is the only even potential candidate for a local maximum or local minimum. So let's draw our number line and see how does the derivative behave around this critical number. Zero and 2 are good test points to plug in. Okay, it was x minus 1, so this is a negative 1 to the fifth and 7th root. Well, because these are all odd things that are happening, I mean, literally odd numbers, 5 and 7. That'll turn out to be negative. I'm taking negative 1 to the fifth, that's still negative 1. I take the 7th root of negative 1, still negative 1. All right, let's check the other side, because it's not a guarantee that the derivative is positive over here. Okay, x minus 1, so 2 minus 1, 1 to the fifth. So this part will just be 1. So this is 2/7, which is positive. So around this critical number of 1, my function f is decreasing on the left side, then we hit 1, and then it's going up from there. So that's a low point, that's like a valley. So that critical point is a relative minimum or local minimum. I'm going to say of 0 because that's the y value. If you check, you plug 1 into the original f. But I'll spare you those details. All right, well, hope you have a good spring break if you're watching this in a spring semester. If not, well, tough luck, I guess. All right, bye.